Thank you.
Hi, Raphael. Thanks for the kind introduction and thanks for inviting me to speak today. I'll just share my slides if I can. Let's see if I can get this right. Okay.
Perfect.
Is that working for you?
Yes.
Perfect. Okay. So yeah, as Raphael just said, I'm going to say something today about knowledge graphs, hopefully going, all the way from the theory through to practical applications. So I'm going to start with a very short historical context, background and motivation. So I could go all the way back to, to the Greeks and start talking about knowledge representation there, but as we have limited time, I'd perhaps better just fast forward a bit to the early days of AI, and knowledge representation and reasoning was right there, at the genesis of AI, with ideas like the general problem solver from Newell and Simon, and then a little bit later the whole expert systems idea. And actually, if we go back to that point and look at expert systems, I found this picture somewhere on the web from way back when about expert systems. The basic architecture of modern day knowledge representation and reasoning systems is already there. We've got a knowledge base which consists of a bunch of rules or axioms and facts, and an inference engine and user queries are answered by the inference engine by reasoning over the knowledge and the facts. So why use a graph? Well, just to pop very briefly back to our Greek friends, I mean, it's a supernatural way of representing knowledge, and it's been there right from the very beginning, as we can see in this little picture of the famous tree of porphyry. And if we jump back again to the early days of AI, graphical forms of knowledge representation were very common then, in the form of semantic networks. And if we come forward a bit further in time, actually it's interesting to sort of look at the World Wide Web and think, well, actually in a certain sense, I can see that as some form of graphical representation where I have these pages scattered about and they're linked by URI links that could be seen as edges in the graph. And actually this idea motivated the W3C semantic web activity, the goal of which, or the idea behind which, was to try to transform this rather ad hoc web structure into something much closer to a semantic network or a kind of huge distributed knowledge base. Okay. And of course, if we come right bang up to date, then we start seeing things like the famous Google knowledge graph. And again, when Google thought, well, we need to represent some knowledge here, what are we going to do? The conclusion they came to was a graph is a good structure. And now we're seeing graphs really all over the place, not just in Google, but all the other big players in the web space, and also much more these days in industry. And I'll come back to that a little bit later in the talk. Okay, so having sort of set the scene and motivated why we might be interested in using a graph at all, I'm just going to introduce a small running example and use that to take a slightly more detailed look at what a knowledge graph, what makes up a knowledge graph, and what we can do with it, make sure we're all on the same page. So the anatomy of a knowledge graph, well, it consists of a bunch of entities and values which make up the vertices of the graph, and these are connected with labeled edges that show how the different entities and values are related to each other. So for example, here, let me just flip to the pointer so that you can actually see what I'm pointing at, I hope. So here we have, for example, the Shard is located in London and it has a height of 310 meters. And if we're in RDF, if we're in an RDF world, as most of us know, each individual pair of entities connected by an edge, a labeled edge is called a triple, with the first entity called the subject, the label on the edge called the predicate, and the target entity or value being called the object. Okay. It's interesting to know, though, or interesting to note and kind of contrast the fact that you could store this information just as well in a relational database. So in fact, I have some tables here that basically capture exactly the same information that I have here in my little fragment of a knowledge graph. But the graph form, we can see some pretty obvious advantages to that. For one thing, it seems to be more intuitive. I mean, when I look at the graph, it's pretty easy to understand what knowledge that's really capturing, or at least it seems to be easy. It's quite intuitive. And more concretely, for example, I don't need any foreign keys to kind of explain to me how to navigate around this table structure, which otherwise would really be quite difficult to understand. Another thing that we can see in the knowledge graph is that it explicitly represents both the data and the schema in the same structure. So outlined in blue here at the top of the graph, I have knowledge that we can think of as schema knowledge, a sort of simple ontology, a kind of taxonomic backbone in this case. And at the bottom, I have the data, and they're all living together in the graph. And it, you know, again, it seems to be quite natural and intuitive. And it means that I can manipulate at least this basic schema information in exactly the same way that I can manipulate the data. Another thing that is nice about the graph form is that there is a unique node representing each entity. Whereas in contrast, in the database form here, we have to repeat entity mentions, like Shard here appears in the building table and the architectural structure table, and Paris occurs in the city table and the architectural structure table. And moreover, these are just strings, and I actually have to use string matching in order to make connections between the different tables. So the information is more scattered about. In fact, in graphs, at least in RDF graphs, we can also use URIs to label our entities rather than strings. And then we can use this kind of linked data idea to actually use common URIs that actually reference other knowledge graphs. So for example, here, instead of, or probably as well as architectural structure, I can label this entity with the Wikidata URI for architectural structure, and then I can actually go off and I can look in Wikidata and get a load more information about architectural structures. Another point about graphs that's sort of obvious or well known is that they're much more flexible and extensible. So I can change the schema about, I can add some additional features, like I might want to add architects to my buildings. Doing this in a relational database is notoriously difficult whenever I have to change the table structure. And I can also delete things from my graph, obviously, just as easily, just by deleting edges. And some of those of you who've been paying attention might already have noticed that I had this edge at the bottom of my graph here that represents the UK's membership of the EU, which sadly has to be deleted. But this isn't a mistake. I'm going to come back to this later because, of course, then we need to think about how, when I have reasoning, we need to think about how I'm going to update my graph when I delete some given facts. And finally, another nice thing about graphs is that they facilitate a lot of different kinds of queries, not just the regular sort of Sparkle query, but I can also have sort of navigational queries, and I can think about things like similarity and locality, which, you know, I can base more generally on structural analysis of the graph. Okay, so hopefully I managed to convince you that graphs are at least not a completely stupid idea as a way of representing knowledge, and so far everything looks good. But of course, as usual in computer science, you know, it's not totally straightforward, and as well as the good things, then some challenges come along. But that's okay, because, you know, we're computer scientists and it keeps us in a job fixing all of these things. So one of the main problems with graphs, which is kind of ironic given that the early graphs were called semantic networks, is that the semantics is terribly vague, actually. So this was pointed out way back when in the semantic networks era by Quillian, for example, and he gave this little example of a graph that, you know, seems to be talking about Felix the cat who's sitting on a mat, and Felix is a black cat. But then actually, when we start thinking about it, this edge here that represents the fact that Felix is a black cat, I mean, that could actually be interpreted in quite a number of different ways. It could mean that, does it mean that all cats are black? Does it mean that some cats are black? Does it even perhaps mean that only cats are black? So, you know, if we're going to do something with this kind of information programmatically, we need to be clear about what the meaning is. So how to solve that problem? And yes, and well, before I start talking about the solution, I can sort of show how in my example graph here, this, you know, sort of comes back to bite us, in the sense that if I have a query such as, give me all those architectural structures that are located in the EU. Well, if I look at my graph as a sort of human being, it seems intuitively that I ought to be able to answer that question. You know, I have the Eiffel Tower, for example, which looks like it's a kind of architectural structure, and it's located in Paris, which is the capital of France, which is a member of the EU. So I should be sort of good to go. But that answer, being able to answer that query with Eiffel Tower as one of the answers anyway, makes a lot of assumptions. I mean, it makes some assumptions about the semantics of type edges and kind of edges, or subclass of edges, if we want to use the OWL terminology for that. And of course, it makes even more general assumptions about the semantics of the combination of location, capital of, and member of edges. So I'm sort of assuming that these inferred edges might exist in the graph, but this is based on many assumptions about the semantics. So how do we deal with that? Well, luckily, we're not the first ones to, you know, to consider this problem. And actually, philosophers, logicians, and mathematicians have been thinking about this for a long time and come up with logic as a solution to the problem. In fact, you know, logic was really invented for this precise purpose, for precisely explicating what we mean when we try to write down representations of knowledge. And in our case here, what we can do, and in fact what OWL and RDF does, is it just defines a mapping from the graph form to a logical form. So it actually, you know, considers the two just to be alternative syntaxes for the same thing. So my ontology part at the top here, the sort of basic taxonomic backbone, I can just map these to simple logical inclusion sentences like this in the obvious way. And similarly for the data part in the bottom of the graph, the RDF part of the graph, the basic facts, I can just map them directly to ground facts in logic in the obvious way. So when I have Eiffel Tower located in Paris, I just have this fact, location Eiffel Tower, Paris, and so on. And this is just part of the specification of OWL and RDF. And this has a lot of advantages. For one thing, oh yeah, and if I take the whole thing together, then it's often called a knowledge base or a knowledge graph. And doing it this way has many advantages. For one thing, I can now extend my schema language to include, I mean, in principle, arbitrary logical sentences. So for example, I can explicitly specify the semantics of this interaction between location, capital, and member of with a couple of additional axioms that say how I think those things ought to behave. For another thing, it actually gives me also a semantics for query answering. So query answering now just becomes very naturally logical entailment. So the Eiffel Tower is in the answer to my query just exactly because my knowledge graph in its logical form entails that the Eiffel Tower is an architectural structure and that it's located in the EU. And we could think of this as alternatively as saying that actually my knowledge graph entails these additional implicit edges that are what then allows us to answer this query. And again, I'll come back to that a bit later when I talk about actual algorithms for reasoning. So another thing about logic is that not only does it sort of define the semantics, but we can go off and, grab a textbook and come up with, a number of algorithms that we can actually use computationally to do reasoning and to answer queries. For example, we might decide to use natural deduction rules, and I could use this rule here to capture this entailment, to actually compute this entailment that the Eiffel Tower is an architectural structure. And if we're lucky, the people who design these algorithms have even given proofs that they do what they're supposed to do, so we can be reasonably confident that we can take those algorithms, implement them, and we'll have at least a correct system. So again, it's the roller coaster ride of research and computer science. We were down, then we were up, we thought we'd solve the problem, but then, we discover, oh dear, actually, this logical reasoning problem turns out to be a very, very hard problem in general. In fact, it's one of the kind of archetypal and it's one of the archetypal undecidable problems, along with the halting problem. And even if we choose a slightly less expressive logic than first order logic, so we kind of rein in the expressivity a bit, as was done, for example, in the OWL ontology language, which is a decidable subset of first order logic, then it may still be the case that the reasoning in that language has a very high worst case complexity. And so that just might take an infeasibly long time. And actually, these problems were really the ones that the early pioneers like Newell and Simon sort of ran into, and that caused those early attempts at symbolic AI to not be really successful. So they look really nice in the lab on toy problems, but then when people tried to deploy them in realistic applications, they ran into these problems of computational complexity, and the systems just weren't scalable. So what can we do about that? Well, we can't obviously change the decidability and tractability results, but we can at least take a more nuanced view of them and realize that, well, in the first case, these are worst case results. So even if our logics are undecidable or intractable, there may still be some problems that are decidable or empirically tractable. And it may even be the case that the realistic problems that I actually encounter in practice are not so hard. And we can sort of run with this idea and basically decide, well, we'll take a sort of two-pronged approach. We'll study knowledge representation languages, and we'll try to find ones that offer a suitable balance of expressive power and computational tractability. So we won't, use every single expressive feature that we can find just for the sake of it. We'll try to, strike a bit of a balance. And on the other side, we'll design reasoning algorithms that work well in typical cases and try to develop highly optimized implementations that exploit the kind of features that we see in these typical cases. And these ideas were exactly the motivation behind the whole research area of description logic. So description logic is a family of logic-based knowledge representation languages. They're usually decidable subsets of first-order logic. And basically, they're sort of modular languages that provide a range of different constructors, and you can pick some of these constructors and define a language as being the subset that supports those constructors. And the description logic community over the years have explored this space, discovered the complexity results for different combinations, and sort of identified sweet spot languages and constructed quite effective reasoners for several of those description logics that seem to occupy some sort of sweet spot between expressive power and computational behavior. And so this was the reason why, coming back to the W3C and the semantic web activity, this was the reason why the W3C decided to base OWL on a description logic, because this description logic in question was the result of long-standing research into the space. They decided to choose this description logic SROIC, which is at kind of the most powerful end of this trade-off between computational complexity and expressive power. I mean, basically, this is the description logic that includes all the features that you can include without actually going over this cliff edge of undecidability. But on the other hand, this language had also been the subject of quite a lot of engineering effort and implementations that were available that were quite effective in practice. Okay, so again, we seem to be, we're on the uphill slope again. We've contended somehow with the challenge of intractability. We've got our OWL language now that's based on a description logic and a kind of apparently empirically effective reasoning solution for that. But of course, there are always still more challenges for us. And one of those challenges was the sort of gap between ontology-centric applications and data-centric applications. So in ontology-centric applications, we're mainly interested in the schema part of the graph. And we're interested in constructing, potentially large ontological schemas. Sorry, was someone jumping in with a question? No? Okay, no worries. Yeah, so we're looking at supporting the construction of ontologies, using reasoning, typically classification, and reasoners such as Hermit and Elk were pretty successful at this, actually, and many of these ontologies are widely used, and some of them have really even had huge impacts, such as the SNOMED ontology, for example, which is used in healthcare systems around the world and has an ongoing large effort to extend and maintain it. But the thing with these applications is that ontologies, even large ones, typically have fewer than 10 to the 6 classes. And in some cases, and in many industry applications, we see these more data-centric applications where the knowledge graph looks rather different. Instead of just having this huge ontology and literally zero data, they tend to have a modest size ontology in typical cases, I would say, but huge data sets potentially. And there can be, in these kinds of application, we're looking at graphs where there can be 10 to the 9 edges or even more. And obviously Wikidata and the Google Knowledge Graph are more in this space, but also many industry applications are more in this space. And the DL developed reasoners like Hermit and ELK, which were very effective in the ontology use cases, are not particularly effective with these huge graphs consisting largely of data. So when the W3C decided to do a revision of OWL to define OWL2, one of the things that they did was introduce this idea of profiles. And profiles are basically just smaller description logics that are subsets of this SROIC description logic, but have better computational properties and that are targeted more to these applications with very large data sets. And the 3 profiles that were introduced were called QL, which actually stands for query language. It was based on the DL Lite description logic, which was sort of focused on query answering. EL, which is based on the EL description logic, and RL, which I'm going to talk more about in a minute, which is based on the kind of fragment of description logic that you can also capture in data log. So it's kind of the intersection between description logic and data log. And the other things, these profiles all had were at least tractable, so polynomial, or even in the case of QL, log space worst case complexity. But they also allow, and I mean, probably because of these complexity results, they allow for the use of different algorithmic techniques. In the case of QL, we can actually use query rewriting. And in the case of RL, we can use materialization. And there's an adaptation of that to EL called the combined approach. And I just want to say a little bit about the materialization reasoning for RL. So actually, the way this works is that we just treat well, I have an example here of answering a query just for architectural structures. And the way this works in materialization is I just treat the axioms or the data log equivalent to those axioms, which are just these rules, which are, from a logical point of view, these two things are completely equivalent. I just treat these as kind of forward, use them to actually materialize into the graph implicit edges that I can derive using the rules. And in this case, basically, it just means I add these 2 additional type edges, which sort of capture this semantic relationship I was mentioning between type and kind of, which is also specified in these 2 rules. And now I can answer this query for architectural structures just directly over the graph without bothering to consider the ontology anymore. So I do all my reasoning ahead of time as a sort of pre-processing task, and then I just answer queries over the graph, and I get that the Eiffel Tower and the Shard are architectural structures. I can answer that directly because of these 2 new type edges that I added to the graph. And I can use this process also for my more complex rules that I introduced earlier and add some additional edges that show that the Eiffel Tower is located in France and it's also located in the EU. And this allows me to add to answer my more complex question for architectural structures located in the EU. So the Eiffel Tower is in that. I don't need to look at the ontology or rules anymore. I have this type edge saying it's an architectural structure and a location edge saying that it's in the EU. So I'm good to go. But obviously what I also get with these rules and these facts is I get that the Shard is in the answer because I also have the Shard is located in the EU. And as we saw earlier, unfortunately, this is no longer the case because the UK ceased to be a member of the EU. But this is one of the issues with this materialization-based reasoning approach. Unfortunately, I also then need to do some truth maintenance. So actually, because this edge is no longer there, this edge should no longer be there. And most knowledge representation systems, most graph databases today that use this materialization approach, unfortunately don't support truth maintenance. So if you delete any edges from the graph, you actually have to just delete all of the entailed edges and then rerun the whole edge derivation process, which can be very time consuming for large graphs. So some of these considerations were what motivated our research into RDF-OX, which was motivated by the fact, well, materialization-based reasoning seems quite a good idea for these data-centric applications. I can support quite an expressive ontology language, not as expressive as the whole of OWL, but still pretty powerful. And also, it allows for very fast query answering over large graphs, because basically I do all the hard reasoning work in a pre-processing step. And then when I come to answer queries, I can answer them very fast. The challenges are that materialization can be costly in time and memory. So it's a pre-processing step, but it would still be good if that didn't take, days or weeks even to complete. And as I was just mentioning in the example, particularly that would be bad if I need to repeat the whole process every time the data changes. So it would be good to have a system that was optimized for very fast materialization that exploited, for example, modern multi-core architecture, but at the same time allowed for incremental maintenance as the data changes, so I can avoid having to repeat this pre-processing step whenever I delete a fact, for example. So one of the things that we also wanted to do with RDF-OX that we thought was really important was to actually base it on formally proven algorithms. As I was mentioning earlier in the talk, when I was discussing one of the advantages of logic is that we have algorithms and we can formally prove that they're correct with respect to the semantics. And early on, we took the decision in RDF to always base the system on algorithms that we proved to be correct. And it was kind of interesting. We didn't carry out this test here, but one of the customers at OST carried out this test when they were trying to decide which graph database to buy, and they compared RDF-OX with 5 other graph databases, which I've anonymized to save their blushes. But what they found was that these other systems, which presumably hadn't been designed in this way using formally correct algorithms, but rather using some sort of software engineering process where they just, fix things till it no longer seemed to break. But unfortunately, it's very hard to design reasoning systems that way because they're so complicated and interconnected, and all of these other systems were really just broken. They were crashing on several of the test queries, or giving wrong answers, or just timing out, or whatever. So I'd refer back to my point that an advantage of logic is that you can use these proven correct algorithms, and you really should do that and not just do some intuitive software engineering. Another thing we wanted to do, as I mentioned, was to try to make the system sort of exploit modern architecture so that the materialization process and indeed query answering could be as fast as possible. So we actually chose to make RDF run in memory so that we could exploit some extremely sophisticated in-memory data structures that avoid locking by using compare and swap instructions and this kind of thing. That does introduce some constraints on the ultimate size of the graph that we can store on a single server. But with modern servers, having potentially very large amounts of memory, we can still store 10 to the 10 triples on a large server, which is enough for most applications, I would say. And as I was just mentioning, this data structure supports parallelized materialization without locking the data structures. Finally, we also went away and looked at all of the literature on view maintenance and truth maintenance, and we found some reasonable algorithms there. The DRED algorithm, for example, is quite good from the database area, but in some cases, it over deletes when you delete facts from the data. So we extended that with some additional features that try to tame this over deletion. And in RDFOX, we use a novel extension of this DRED algorithm that we call the BF algorithm, because it does some backward chaining deletion, but then some forward chaining checking to see if it can find alternative derivation pathways. So that's about all I've got to say about RDFOX. So except for the fact that actually I forgot there was this one extra bit that I put in the talk, just to say that was what we did in research. And then we were motivated to develop this system into a product, because we really wanted to be able to support people in industry that were trying to use RDFOX. And what we discovered there is that there's actually quite a big gap between theory and practice, as I'm sure many of you out there know already, particularly those of you that actually work in industry. And on the one side, it turns out that the language specification that we started with, which was OWL-RL basically, and data log, misses quite a few features that you really need to use in practice. And in particular, I haven't got time to go into all of the things here, but one example is data types and values. So actually in OWL, OWL includes all of the XML schema data types, but it doesn't say much about manipulation of data types. And actually, this is really a huge part of many realistic industry applications. So not only do you need to represent numbers, strings, and dates and so on, but you have to have a bunch of built-in functions for doing things like pulling the year out of a date and concatenating strings and aggregating numeric values and all of these fun things. So what we did in RDFOX is we basically took a lot of what was in the Sparkle spec, which has much more to say about built-in functions and aggregation and so on. And we support more or less the whole of the Sparkle query language in rule bodies. So we can actually, in rules, we can do much more about manipulating data values. And another thing we found was that in many realistic applications, you need not just material implication, but also constraint checking. So quite often in applications, they don't really want to derive new facts. They want to check that the structure of the facts that have been explicitly given satisfy some constraints. And for this, basically, you need some kind of negation as failure, which we also added to the language that is supported by RDFOX. And the other side of the coin is system architecture. So when we finished developing RDFOX in the lab, it looked like this. It basically just had a reasoning engine with a Sparkle API and a command line interface. But of course, to turn that into a product, you need to surround it. You need to extend it with various things like persistence and a web console and blah-de-blah, and surround it with a whole bunch of infrastructure, interfaces, running on different platforms, and all of the things that, as kind of university-based researchers, we hate to do, but actually really need to be done before you can have a product. And it took probably 2 years, I think, to go from the lab-based RDFOX to the commercial product RDFOX. And just before I finish, because I think I'm running out of time now, I'm just going to mention a couple of use cases or even actually really just one interesting use case. So, I mean, obviously there are all the, the sort of web-based use cases like Open Q&A and semantic search and browse, but I just wanted to come back to talk about an industry use case. And actually in the company, we're seeing a lot more of these kind of industry use cases that have been around for years, but that I think semantic technology and knowledge graphs can go a long way towards being able to solve. And one example is configuration management. Again, this problem has been around for many, many years. I recall it was one of the problems that was being addressed by the team working on the classic description logic reasoner, which some of you that are as old as me may even remember, but most of you probably don't even remember that. But that was, I must be talking 40 years ago here. And again, I think basically that was a good idea, but they didn't quite have the kind of reasoning technology and the computational muscle to solve the problem in those days. But now configuration management seems to be quite a nice application that we can address with knowledge graphs. And one example is at Festo, where they're using RDF-Ops for exactly this purpose. They have a huge number. So Festo, in case you don't know, is a German-based multinational that produces these kind of robotics and production line equipment systems that are huge and incredibly complicated. And they have a vast number of different components in their catalog, and they need to kind of assemble these into bespoke systems for different customers that cost millions of pounds. So it's, it's really important, probably tens of millions of pounds. And it's really important to make sure these systems are correct and work when they install them in the client. So they also capture a bunch of kind of expert knowledge about configuration, compatibility, and so on, using rules, for example, that capture the fact that if I have a motor and I have a power supply, then that power supply should provide the right kind of voltage, the right amount of voltage, and at least as much current as I need in order to drive the motor. And if all these things are satisfied, then this motor and power supply are compatible. Okay, so to wrap up, what do we have? Well, in summary, I could say that knowledge graphs are a very powerful tool for representing and reasoning about knowledge. There are many applications. I showed you configuration, but there are also applications in data integration, compliance, financial services, a whole bunch of them. As I mentioned, there are many technical challenges which we've had to solve along the way, but hopefully we've managed to solve most of these problems by combining foundational research and solid systems engineering. So that's about it for me. All I want to do now is to say thanks to the many colleagues and collaborators that I've been working with over the years and whose work I've been presenting here. And say, thank you for listening. I'll be happy to answer any questions that you might have.
Thank you so much, Ian. That was great.